All right. Hi, everyone. Sorry for the couple of minutes of delay and the delayed start of the talk. Today, we're very happy to have Bowen from UIUC visit us and give us a talk on modular flows, Chiral central charges, and the edge CFTs. Thank you so much, please.
Great, thanks for the introduction, Nima. And it's my great pleasure to be here in Purdue. Actually, this is my first time visited in my 12 years in the US. I always you find many friends from Purdue actually when I'm back working in high energy groups. But now finally I get a chance to visit, and I'm excited about it. This topic, modular flow, Chiral central charge, and edge CFTs is some mixture of idea from high energy condensed matter and quantum information, and I can recognize some of your faces from high energy and from condensed matter, and yeah, and people are interested in quantum state. So hopefully, I will make it way that's accessible. If not, please ask questions. I have experience to talk to different people with different backgrounds. Hopefully, it will be interesting feedbacks from you and questions. Okay. So today, I will review some of the ideas from a multi-particle quantum state. What can we consider? Like consider this tensor matrix. We can consider entropies and so on. But modular flow is actually an interesting idea, which is still not fully explored. And especially on part 2 and part 3, we're talking about two unpublished work. You cannot find it on arXiv. One is nearly finished about something I draw in this picture, some sequence of a modular flow. Another is a question I thought was intriguing and deep, and that question has been asked during my years in San Diego when I collaborating with those wonderful people on some other projects on chiral edges. But now after I moved to UIUC, I started to talk to local people with high energy background, like Tom Faulkner and his student and postdoc. And we chatted with Nima. I chatted with Nima indirectly because Jing talked to you at some point. Okay. So first of all, I would like to emphasize some similarity and a slight difference between high energy sense of a many body system, quantum field theory, and condensed matter system. So for high energy, usually we have a space-time to play with. Sometimes it's flat, sometimes it's curved, but you have space and time, so you can draw those slides in space-time. Here is a space-like slide and call it cozy surface if the boundary is good. Every time like curve is exactly with it. And the causal diamond, those are nice things because you have light count. And if you want to understand the entanglement in field theory, you can play with those ideas. In condensed matter, what usually happens is that space and time will be treated differently. You have a wave function on lattice. You can spread your qubits on a two-dimensional lattice, 3 dimensions, depending on what system you are interested in. And you have a wave function. So there's some locality either in the Hamiltonian or sometimes in the modular Hamiltonian for some reason. And there may not be Lorentz symmetry for that system. However, if you are interested in the low energy effective theory, sometimes those symmetries and so on emerges in some way. The word emergence is quite deep. But okay, those are the background I want to emphasize. Today I would most of the time I will be more like a condensed matter, but I will borrow a lot of tools from field theory as well, or some version of it inspired by it. Okay, so let me first give you a review of a modular flow. This was the simplest case. So by a modular flow, I'm considering a setup which is simpler than what people consider in quantum field theory. For quantum field theory, you can think about a local region, but then the Hilbert space won't be in a tensor product with the rest of the world, and it's an infinite dimension. But let me be slightly, make it a simpler setup that many quantum information people would like to consider. It's like a Hilbert space on A and B within a tensor product. And I will, most of the time will assume the Hilbert space is finite dimensional. And now you suppose you have a pure state on a system, tensor product Hilbert space. We can cook up this kind of thing that evolve the state. Question? Is there a question? Okay. So it's like we start from side B. Suppose we only know this single pure state. What can we do? Because we know the partition, we can, evolve the state by a modular Hamiltonian. By that I mean Ka equal to minus the logarithm of the density matrix is some operator, information operator, like a Hamiltonian. So we call it a modular Hamiltonian. Condensed matter people call it entanglement Hamiltonian sometimes. And so it's so e to the some I imaginary real parameter s, and the modular Hamiltonian is actually a unitary evolution. So you're doing some unitary on the subsystem, and therefore you get another pure state which is perfectly normalized, but depend on the real parameter, so we call it psi of s. Well, the familiar von Neumann entropy, well, we can define this by minus trace rho log rho, but it's actually also captured by the modular flow, but in some somewhat trivial way, that s goes to 0 is enough. When you evolve the state a little bit, then you see some difference. That's the entanglement entropy.
Sorry, technically what you've written there is a co-cycle flow, right? Because modular flow, if B is a purification of A,
Okay.
you would write rho A to the power of IS tensor rho A bar to the power of minus.
Yeah, exactly. That's the thing I wanted to comment, but it's not showing in the slide. It's like in the full field theory context, we don't want to mess up with the cutoff, so we evolve some region in positive parameter, but the complement will be evolved in the negative parameter.
For sure, but for your second equation,
okay,
this von Neumann thing, it is important that you have the half-sided modular flow there. Right? If you put the full modular flow, it's a symmetry, so you won't do anything.
Right, that's right.
Yes.
And in that context, what's important is that version of modular flow you talk about, when the field theory talk about, is automorphic, some mapping on the operator algebra, but it doesn't evolve the vacuum.
Absolutely.
Yeah, good. Then I'm talking about the version with the cutoffs. Yeah, good. All right. So suppose we have a quantum field theory with some cutoff. So the cutoff is epsilon. Yeah. For condensed matter people, it can be some lattice cutoffs, but it can be some other things. But you have this nice formula with the CFT central charge and logarithmics of the interval, single interval length L. So L is dependent on the A. And for two-dimensional one, you can think about these as some topological quantum field theory, but most of the time I will think about some lattice model, realize something called topological order system with some anyons. Then people can consider this some clever combination, linear combination of entanglement entropy. So each S of some subindex is some von Neumann entropy computed for the region for that particular state I'm interested in. The gamma. It turns out this way, what you extract is the subleading term of the entanglement area law is, according to those people, is perfectly quantized to give you the total logarithmic of the total quantum dimension of anyons. So you get 0 if there's no anyons in the system. You get some positive number if there are anyons. The counting of how many anyons there are in the system. Well, those are some nice formulas in terms of entropy. So as I said, it's some limiting case of this flow, either quite modular flow or co-cycle flow. And now, well, this is a bipartition. You don't have many choice of what to evolve. You evolve according to the density matrix on A. It's actually the same with evolve according to the density matrix on the complement, the B. But how about multi-partite system? Actually, we have more choices, as I will say here. So if you have a Hilbert space that's tensor products of many, maybe 3, 4 different other numbers of parties, you can have a union of any such regions. I suppose it's tensor product Hilbert space. Evolution according to that region is like this, is similar. But now you can consider a sequence of modular flows and regions. An naive generalization is the following. You take this state, consider its reduced density matrix rho B, rho BC from the same state. We evolve by parameter T and then by parameter X, first on BC and then on AB. Yeah, it's something maybe too naive. Maybe you are already not so happy about
This is wonderful. This is wonderful.
Okay. Yeah, anyway, so there is something people can think about. Yeah, if you know the single state, indeed you can do such thing, right? There's no problem. You have unitary and unitary, why not? And actually, indeed, you can use this idea to come up with something very, very interesting, as I'll explain. But let me first define it. So you find some small parameter of S, you evolve it on BCAB, and then evolve back on BCAB. This sounds very familiar if anyone have learned Lie group, right? In Lie group, you have this epsilon, you have this nice commutator Lie algebra, right? We can play the same trick here. So it's like this modular commutator. It's it feels like a generalization of the idea of a Lie algebra Lie group. But we are still not exploring the full thing yet. If we have S goes to 0, we take the limit, we get this thing I call modular commutator. I haven't tell you why this is interesting, but I will do it in 2 pages. First of all, this thing is the pattern is introduced pretty late, and I was involved in the project. This formula is like any mixed state on rho ABC. You take an I trace rho ABC and the modular commutator. Yeah, the commutator of modular Hamiltonian. In other words, just the expectation value of the commutator of modular Hamiltonians. And before I tell you the many-body context, I can already tell you several things that make it interesting. And first of all, is chiral. And chiral under time reversal. But by time reversal, I mean if you have a rho, it's a density matrix, you involve complex numbers. In the right local product basis, you have a complex coefficient. You mix the coefficient to the complex conjugation. You get another state. We can call it rho star. And if you consider J for the rho star, you get a minus sign. And if you flip A and C, you get minus sign. So it's like the idea of chirality. You have something very similar to another, like a molecule and its mirror image, but they are different. You cannot rotate one to another. And what cannot be rotated? The rho and rho star. So if modular commutator is not 0, the rho and rho star cannot be related by conjugation on product of a local unitary. So you have UA tensor UB tensor UC. You cannot rotate rho to rho star. And it's a response of an entropy. So this picture might be somewhat simpler than what I showed in the previous page. So this is one way to think about, but another way is that you evolve the state somewhat, and then the entropy of another region changes. It's the change, you ask what's the rate of change, it turns out to be the modular commutator. And another nice property is that if you have so-called Markov quantum Markov state, well, quantum Markov state is a tripartite density matrix such that the condition of mutual information defined here is 0. The condition of mutual information is always greater or equal to 0. When it's 0, many nice things happen. This is one of the nice things. We have a 0 modular commutator. And those are some other properties you can think about, but let me omit this part.
Sir, quick question. So the Markov property will also give you an operator equation.
Yes.
And does that imply that the commutator rho BC and rho AB is 0? So not only the expectation value, which is J, is 0, but also all the higher moments are 0. Is that true?
Actually,
I thought it was true.
Let me think about it. So the proof is the following. So you have commutator of rho AB and rho BC. Now you replace KAB.
Correct.
But replace KAB by KABC minus KB minus KBC. But then you have some terms. One is commutator of KBC with KBC.
Yeah.
Another is KB with the KBC. I'm not sure that's 0, but
Okay,
when we take
we can discuss this
Yeah.
afterwards.
yeah, when we take expectation value, I can say for sure because I can deform the modular Hamiltonian to the complement.
That's right, that's right. Yeah,
Good.
that's right.
All right. Now here is the one important reason, at least one reason we are very interested in modular commutator in about condensed matter people. As a condensed matter people is well motivated by the following phenomena. It's actually observed in impairment as well. It's like you have some gap for dimensional system, and suppose it is chiral, so there is something called chiral central charge, which is effectively capture the boundary phenomena of the difference between the number of left moving mode and the right moving mode. It's called C minus the chiral central charge. It could be positive, it could be negative, depending on whether you have more left movers or more right movers. And when it's non-zero, it turns out the equilibrium state is interesting. So you have an equilibrium state at a very low temperature. The temperature is lower than the bulk energy gap. And it turns out the boundary has a very nice formula for the energy current. Energy current only goes along the boundary is pi over 12 chiral central charge times temperature square. Temperature square, I believe I said h bar Boltzmann constant to 1, something like that. And therefore, this number is very important. And people believe this can only take rational numbers. And a puzzle is how to compute this quantity. Obviously, it has something to do with the bulk because there is another thing condensed matter people usually say is that if you have a purely one-dimensional system, in the sense that you have a tensor product of a space and local Hamiltonian, and at any temperature, the energy current must be exactly 0. And we disagree with this formula. That means this non-trivialness come from the bulk. How can we extract this important number from a bulk wave function, the ground state wave function? So we came up with this formula and we argue this is true based on some argument. I will say it's not completely in the mathematical rigor, but we have a way to argue it's proportional to chiral central charge and theoretically try to fix the coefficient to pi over 3. And it's a physical success. And we tested this in different models. One is an analytical wave function, discovered by, considered by those, I think invented, discovered is maybe a better word, by those people in Europe. And actually this wave function came up again and again in the later topic of the day. But when we tested this on some analytic wave function of interacting bosons with anions in the system and chiral, it works well. And the formula is also tested up to like 5 digits in free fermion system on very large size. But let me omit this part. So we have a nice formula from the bulk. It turns out the next year we did something for the gapless edge as well. So if the edge is described by a conformal field theory, then maybe we can see similar chirality behavior near the boundary, which might be different. Somewhat quickly we were able to test and argue this formula is true. So if you take the 3 regions near the boundary, so it touches the 3 regions, touch the boundary at the 4.1, 2, 3, 4. You know that on a circle, if you pick 4 points, and suppose the series conformal is a very natural to talk about cross ratio. So this atom will be the cross ratio involve the 4 points. It turns out the formula is modified by just the original formula times the cross ratio. So if ABC covers the entire edge, the cross ratio will goes to 1. You get actually the same with the original formula, but this one is geometrical dependent. We first argue with some CFT assumption, but later we replace the CFT assumption with some locally checkable condition on a single wave function. It's more like an entanglement bootstrap flavor, and the other work is more like a CFT-based framework. And one nice thing about this, I don't need to emphasize, but in this talk, but the nice thing I enjoyed when doing this work was that we don't need to assume the distance measure, but we can somehow show that the conformal cross ratio emerges from some other physical assumptions, so that seems to be simpler and has less structure. Okay. Any question? This slide is pretty dense, I believe. Okay.
So can you say a few words about that physical assumption?
The physical assumption, actually, it turns out there are two versions of the assumption turns out to be equivalent. One is a vector-like equation. Is some linear combination of modular Hamiltonian acting on the state and proportional to the state. But I cannot write it, or we can talk about it later. It's equivalent to another one, which might be easier to say. It's we can define some function, we call it as C, or something we look at it compute, and we call it C, but it's some central charge candidate, but we can have a well-defined procedure to define it using a local wave function and the local partition. And suppose that quantity is stationary under the deformation of the state. Then it turns out this follows, and the number C will be uniform everywhere on the chain. So it's again, some emergent uniformity or something. Yeah. Okay. Now this slide is somewhat away from the idea of modular flow. Why am I telling you about this in a talk talking about the modular flow? I'll tell you, I believe, very soon. But let me give a detour about the intuition on why this formula might work. So some of you, especially condensed matter people, will know this paper by Lee and Daniel about entanglement spectrum. Their idea was very simple. You take your many-body wave function. Well, it must be a field theory with cutoffs, effectively. Or it's some lattice Hamiltonian, or even fractional quantum Hall. They take some region and consider the reduced density matrix. After that, they diagonalize the matrix and find the spectrum. Well, they were somewhat lucky. They can label the thing by momentum, but the important thing is that the entanglement spectrum is not flat. If the entanglement spectrum is not flat, then the modular flow will change the state. So here is a hint. So maybe we can think about some partitions that make the entropy change. And this idea came in the work I did with Etta Kato and Albert. And so those partitions, some of the partitions are, let me try to evolve the state according to the density matrix of the large ball, the yellow ball. And then we try to ask the question like, how does the entropy change on those colored, darker colored region? I believe you can guess that if the system is chiral, then chiral choice of the region may get different non-zero value of the response of the entropy. It turns out that that's the case, and you get 0 for those symmetric choices. Okay, but then this configuration looks different, but the idea is that you can somehow deform the region smoothly into this tripartition of the disk. And why is that possible? That's the next thing I want to tell you a little bit about. That's from the idea of area law, entanglement area law. Well, I guess high energy people were the first group of people use the word of area law is for the black hole, but here is for the two-dimensional system. And sometimes the word area law sounds confusing because each region has some area. But here the area doesn't mean the area of the two-dimensional region, rather it means the area of the boundary of the region. So it's the line, the measure of the length of the line. If you take that sense of area law, you will believe those two conditions make sense. So I guess I've got to write the thing. So the first one is the entropy on C plus the entropy on BC minus the entropy on B is 0. The other condition says the entropy of BC plus the entropy on CD minus the entropy on B and minus that on D is 0. Those are natural to consider given area law, and we actually take this as the axiom, and we can derive a lot of things, it turns out. Therefore, we call it the entanglement bootstrap.
So A1 condition is just CMI being 0. Is that right?
It's stronger than that.
It's stronger than that because you have to take the complement. Is that why?
Yeah.
I thought it's
so yeah, when we talk about CMI, you need to choose 3 regions.
Yeah.
You tell me which 3 regions you are choosing.
I was under the impression that this condition you guys wrote down for A1,
Yeah.
if you allow me to consider E, which is the purification of everything, I can write as a CMI for those
That's right,
regions.
that's right.
That's right? Okay, I see.
Yeah.
And then A0, can you say the condition again?
Entropy on C plus entropy on BC minus entropy on B is 0.
So BC is B minus C?
BC means B union C, so you
Yeah.
have a large
But
disk.
BC, entropy of BC is entropy of C minus plus B?
No. The BC has a large volume,
Right.
but the area is
Right.
just one circle, and the area of C is 1 circle, but the area of B is the largest. So
Right.
we
right.
need to have SC plus SBC minus SB.
Okay.
Yeah.
Thank you.
Great. Yeah, indeed, some implication would be, or you take A to be somewhere in the complement, then the mutual information between AC will be 0. Conditional mutual information, AC condition on B is 0. And in this figure, this axiom A1 implies the conditional mutual information between C and A somewhere in the rest of the system. Condition on B is 0. But those conditional mutual information are strictly weaker condition than this one. Actually, recently in thinking about mixed state topological order, we take those weaker version of the assumption, and there is some version of entanglement bootstrap you can play with.
But there is a very nice operational interpretation for conditional entropy in terms of cost of so-called state merging. So, yeah,
By state merging, you mean?
state merging is a quantum protocol
Mhm.
that they could define. That's Jonathan Oppenheim and friends did this back in like 2010s.
Mhm.
And this problem has a very operational interpretation.
Uh-huh.
So we could talk about this later. Yeah.
Okay, great. Right. So when entanglement area law holds, well, if you have those some axioms on some bounded scale, some finite length scale, it turns out you can immediately prove using a strong subadditivity that the similar, if you partition the larger regions into similar looking partition of this, the similar conditions hold on a larger length scale. So it's a kind of like saying you're already in a RG fixed point for in some sense. So this I think is a pretty deep, because it suggests that you don't need to look into the really infinitesimal detail. You start with some finite length scale, then you know the rest. You know much larger length scales. Okay, with that, it turns out there's an emergent homogeneity. So you can deform one region. So you can think about a convex set of states carry the information of topological charges in the middle. You can deform the region by applying a sequence of quantum channel. The deformation is related to axiom A1. So it says, okay, let's check the axiom everywhere. So if axiom A1 is true, then that means you don't have a domain wall, so you can transpose the information smoothly from one place to another. Is that type of intuition? And you may like to compare this to Noether theorem. The difference is that we don't have symmetry groups, but somehow the fabrication of entanglements, so if it's satisfied some nice conditions, we can actually still transport the information. And another feature of the framework is that we can show the quantization of something important. So the topological entanglement entropy is a sub-leading term of the area law. Previous work said, oh, this should correspond to the anions. But here we can rigorously establish this intuition. We can prove theorem saying some values of the sub-leading term must be forbidden, but it's not forbidden by the topological quantum field theory description. We are not assuming the lattice model will be the straight model, but it's forbidden. The quantum mechanics itself is just consistency relation from strong subjectivity and other things about multipartite quantum state. From there, we can show that some regions are forbidden. That's the surprising part. And yeah, it's only did in the fusion rules from entanglement, the paper we wrote with Ada Kim and Kotaro Kato in 2019.
Very quick question. You said there are no domain walls. I thought
Right.
you could think of SPTs as like a sum over all domain wall configurations. How does
That domain wall configuration you refer to will correspond to some classical configuration. You have spin up, spin down.
Okay.
Yeah. Yeah, that's why I won't call it a domain wall. Yeah.
So you're saying that there's no model, quantum mechanical model where the T can be between 1 and 2, for instance.
Yeah, so exponential of this. So it's like a between 0 and log square root of 2. Yeah, there's no such model, so we can prove that.
So what is violated? Is it strong subjectivity that's violated?
Strong subjectivity and properties of quantum Markov states. Well, we have the axiom, and as you
Oh.
point out, if we have the axiom, we have a lot of different Markov states on different partition. It turns out
Is this for infinite size system, or
this-
does that prove that like T cannot be, it has to be quantized?
okay, that's a very interesting question. Actually, we need the volume. So imagine you have a lattice, which is 100 by 100, and on each order 1 block, I mean, maybe union of nine squares, like a larger square, 3 by 3 square. You have all those conditions checked. Then we can show that within this 100 by 100, you take any partition of the level 1 partition, Kitaev-Pascal partition, the value you get must be quantized in that way. So we actually only need a finite system to give the bound.
And do you need a gap for that?
No, we need a Markov gap in some sense. It's like you can consider some, well, those axioms, I said the right hand side is exactly 0. That's a lie. What the case we really want to deal with that with small errors. We believe that on physical ground, those errors will decay when you cross grain the system, and as long as you have small error, those value will be approximately quantized. Yeah, that part is in progress, but we believe we have that, almost have that in some sense.
So sorry, just to understand. So you have the topologically trivial case, which is the Markov state, and you have the states that are not Markov.
Right.
Now you're comparing the CMI of the non-Markov one and the Markov one.
Yeah,
correct?
Something like that.
So if you subtract the two CMIs,
Mhm.
it's something that people call an inequality that's called it's called the super additivity of relative entropy. I guess I'm wondering if this is a consequence of that.
That's something we can discuss further.
Yeah.
But currently my intuition is the following. In terms of the quantization is related to this convex set of state we can take on the annulus. We show that the convex set, the shape is quantized. It must be a simplex with either one extreme point, which is a point, the two extreme point, it looks like an interval triangle and so on. Because of this quantization and the fact that the vacuum must be the minimal entropy state of the convex set. Using those things, we can show the quantization of this by converting gamma to the memory capacity, to the entropy difference between the maximal entangled state in the convex set and the minimal entangled state in the convex set. That's why it's bounded in a very strict way. All right. And now the philosophy is the following. So if we have a state satisfied those two conditions anywhere on any little balls, then the subleading term defined like this, and the parallel central chart defined by the modular commutator, it should not be arbitrary. Well, condensed matter people had some good idea on what phase should exist, which ones should not exist, and we can treat that as a guiding conjecture. From there, we will say that, okay, maybe only some value of gamma and the chiral central charge can be consistent with quantum mechanics. I already talked about the fact that we have groups for this vertical line, so the quantization of gamma is more clear at the moment. Yeah, it has been several years. But then the quantization of a chiral central charge from the modular commutator remains a deep puzzle. So even solving this for the horizontal line, like taking the gamma equal to 0, a system with no anions, people call it invertible state. Or in high energy, maybe people call it invertible EQFT. But let's take some assumptions in this flavor. Can we show that the modular commutator can only take a certain value but not the other value? Can we exclude some of those parameter values of C minus? That's a deep question. It really makes us struggle. All of us struggle, but it's something everyone wants to solve. I couldn't come up with good answers, but I still want to think about this from time to time. So I could have a simpler problem to think about, maybe will help.
Sorry, is the left picture a typo? CBV, usually the figure, the picture.
Yeah, thank
Okay,
you.
that's a typo, okay.
Yeah, we need B to be union.
Yeah, but that's a standard thing,
Yeah.
okay.
Because then AB will be a disk, BC will be another disk.
All right.
Oh, so this one also satisfies that. So then, anyway, so yeah, we need to do some switch. Thank you. All right. The part 2 is the instantaneous modular flow. Some slightly fancier, but maybe that's the most natural thing. Maybe you already expect in some way. But yeah, the project with German Greavy and the two amazing students, Xiangli and David, yeah, Ding. And okay, I made this art, by the way, because I'm fascinated by this equation. With both gamma and J shows up. The gamma and J were the two things in this diagram. J is proportional to C minus. Okay, I'll try to explain this and why we find this exciting. My personal motivation is to solve the puzzle of quantization of a chiral central charge, but I admit that we are still some distance away. Maybe it's a long distance, maybe it's short. We just don't find the full idea yet. But this one made me think that we will learn something new about the density matrix. So let's go back to this naive generalization. So you have a multi-partite quantum state, and we can do flows on different parts. One idea is to use the original density matrix and do it the sequence of rho to some power. But then another natural generalization is to first do this rho is the density matrix, reduced density matrix of psi. But then after the evolution, the new observer or anyone look at the new state will say, why not we evolve according to the new state, right? That's a natural idea. So this time we add tutor to the second evolution, and the tutor is based on this new state, the state after the evolution. And we will call it some evolution on BC, evolution on AB. Yeah, develop that type of notation. And that's a formal definition of instantaneous modular flow. The sequence of modular flow on different regions, the regions may have overlaps. And the nice property is that if you have a sequence of modular flow, and if you have two nearby regions, and one is strictly contained in another, you can swap them. Oh, I guess this is another typo. The T will be T because I just bring this to there. Yeah, and yeah, so B is S, so this would be S.
So what is a local move? Well,
Local move is to swapping two regions if there's
there's an inclusion.
yeah, if there's an inclusion. Yeah. Yeah, the other more naive version don't have this property. Yeah, I mean this version does not have that property. Okay.
Sorry, I'm a little bit confused. Wait, sorry. Is KAB and KB or KA would not commute in general, right?
They don't,
They don't commute, so why is this move allowed?
because they are acting on a state. The state is exactly the state that defines that density matrix. Then you can deform that to the complex.
Because you could basically, like tensor
Yeah.
networks, push it to the commutant.
Yeah.
Oh, I see.
Yeah,
Okay.
it's here.
Oh, there we go. Okay. Good. So
Yeah.
use the commutant.
Right.
Wow.
All right. So maybe this part already convinces you that there's some beauty in this choice of divination. But next I will try to convince you that there's some beauty in actually applying this to a physical gap system. Consider chiral topological error diagnostic is something with the area law. Yeah, in two dimension, with Q based on the two dimension. I told you about the modular commutator. But then natural question, especially based on this interesting work, vector fixed point equation for one-dimensional CFT. Then how about a vector version of modular commutator? Can we do this acting on this operator commutator of K acting on psi? Is it proportional to psi? We ask this and we test this. The answer is no. So we get this frustrated face. But then a few months afterwards, we ask, oh, how about do this according to the state in each step. So we do this evolution and take expectation value is almost 1. So it means the state always almost evolve back to itself. There's it's not evolved to another state. That was a surprise. We say, oh, this is something so interesting that why we didn't discover this is the first time. So this is a slightly embarrassed face as well. Okay. And then well, for realistic systems, there's errors to the axioms, so we cannot evolve the parameter, take the evolution time too large. It's like take this to be 30, it doesn't work, but small enough it works. But if we take larger and larger region, we expect the evolution time will be larger and larger. That's a
I'm a little bit confused. So looking at question 1, right?
Uh-huh.
You're gonna take a Markov state, right? So I can use KBC is KB.
no.
No, you're
For
not.
this partition ABC. But this partition is not a Markov state.
I see. Because if it were a Markov state, it would be just 0.
Exactly.
Yeah.
Yeah.
I see.
Right. Then we ask what might be good thing. So we take inspiration from the linear combination of entropy and modular commutator. That's the beauty of this choice of regions. It's because they are chosen such that each boundary is evolved to some parameter and evolve back. So we try this those are 2 examples of our result, which are the most intriguing ones. Simple equations. Can we prove them? We can come up with some argument which explain what we observe numerically and agree with those equations. They are satisfied with the high accuracy. We believe they are true, but the complete rigorous proof is lacking because on any finite dimensional Hilbert space, we also the same list of authors. We had an argument that on any finite dimensional Hilbert space, axiom A1 cannot true exactly if we want non-zero modular commutator. So there's some challenge on the mathematical part, but we believe we are making real progress physically. Okay, that's the second story.
Sorry. Can we go back? You are almost getting a Lie algebra here, right?
Yeah, that's the thing. I thought it's more like a Lie algebra, but we need to evolve according to the new state. It turns out we are changing the operator. It's not.
But that's okay. We could do that in Lie algebras as well.
Uh-huh.
Like you could, the same way that you were talking about SO3, you could do the, what is it, like when we decompose SO3 into 3 rotations, the Euler angles. The Euler angles are after, like you do, it's a similar thing. But that T squared is a thing that's very confusing.
Yeah, there's a T square and linear in T.
And then the J operator is what?
J is the modular commutator of ABC. J is the number.
Like what I'm saying is that if you took this expression literally and use BCH,
BC
Baker, Hausdorff, Campbell,
Okay,
So these are a bunch of exponents multiplied each other.
yeah,
It requires some magic to
Yeah.
get the right hand side.
that's right. I couldn't precisely formulate the magic, but if you could, I think it's something valuable.
I think it's just must be the algebraic structure. There's nothing else I can imagine. But yeah, okay. Thank you.
Okay. Well, I do believe there might be something beyond the algebra, but yeah, we should chat about that. Yeah, it turns out even when we look at the infinitesimal version of the previous equation, the modular commutator J flow equation, we get something interesting. There's a correction. So we said we field when we do commutator acting on psi is not proportional to psi. Turns out we can correct it by something interesting. So this kappa, AB BC slash BC, the limit of some, it's like some evolution of the modular Hamiltonian with the parameter of evolution of another region. So why this term comes in? It's quite interesting. Yeah, there are many questions to ask, but let me stop here about this project because I need some time. It's maybe almost the time. So when should I stop?
Look, we have how many more minutes you need?
If I have 15 minutes, it is
That's good. Yeah, that's good.
Okay.
15, yeah, 15 minutes is good.
Then we have the faculty cooking.
Yeah, so we have to leave at 3:25 latest. We have 15 minutes. So one quick question, just a comment. There is something in high energy literature that people called the modular Berry phase. This is pretty much a similar thing we do over there, and it has to do with holography. Yeah, but
Okay. Actually, because of I want to cover the third part of the talk, I deleted some result from this work. It's actually, according to this evolution, whenever you can evolve the state back to itself, you can also define some Berry phase, which is actually different from the instantaneous modular flow phase I'm talking about.
Of course. Yeah.
Is
And there's a
that
curvature. That's precisely what you do. You take a region,
I see.
you evolve it by modular flow of a different region. And there are gauge choices to make. It's a long story. I can tell you more about it.
Okay.
You basically, the idea was that this was used as a way to reconstruct the bulk geometry and holography from the boundary data. Yeah.
Okay.
Yeah, sure.
Yeah, tell me about that. Okay. All right. Now I get to the third part. In some sense, it's my favorite because I used to study gravity before I even was sitting in the field theory class. The general relativity, special relativity was the type of thing I'm interested in. A long time ago, and I think everyone knows about this, right? So it's like space-time are relative, and if you do Lorentz boost, yeah, you is here, your friend is boosted, and there is a famous debate on who is squashed, right? So obviously, this guy is squashed. Is that true? From that person's perspective, the black colored friend is squashed. Yeah, so that's the relativity. But now let's ask a similar question. I'd like to ask the following question. And so you have a vacuum state and some kind of topological order on the disk ground state. And you have another state. You will describe it as somewhere you have an anion sitting there and an anion string pulls out to the boundary. The reason you have a string that pulls to the boundary is that you have anion cannot be created alone. You have you have a bar. You pull a bar to the boundary and try to minimize the energy as much as possible. You get another state. I call it a psi of A. The question is the same flavor with this one. Yeah, this question was who is squashed, and this one is who is a vacuum. But the answer seems to be obvious. This one is a vacuum. This one is not. But are we biased? Are we like this guy? We think we got the right vacuum. Maybe we are not. That's the puzzle I'm putting forward. Yeah, I think it's a very simple question. Hopefully it's deep. Yeah, so as I said, it's actually partially motivated by Nima's work on computing something. I will talk about that. I want to get there. Okay, but let me first start to ask a question. So question one is actually the 1+1 dimension rational CFT version of the question. Your previous page I draw the chiral state on the disk, but this one is nice. So one plus one dimensional conformal field theory on the circle. As you all know that conformal field theory, you have vacuum state, you have primary, and so on. So let's suppose that the primary carries a Bayesian superselection sector. I hope this one will make sense to people, but I will give some examples. Yeah, so of course those two states, the ground state and the primary state will be orthogonal. They are different eigenstate of your Hamiltonian. So you can distinguish them, but that doesn't mean you know which one is a squash them, which one is the ground state, unless you know the Hamiltonian. Yeah, so okay, I guess I should ask this question. Raise your hand if you think those two states can be distinguished. Just knowing the two states.
I don't think they can be, right?
Sorry?
They shouldn't be able to, you shouldn't be able to distinguish them, right?
Oh, okay.
Do you disagree?
I actually agree.
Okay.
But I was expecting most people have a different answer because I would keep asking this question to people.
All right, okay.
Most people get the wrong answer, to be honest. But yeah, that's why we are talking to you about this.
So
Maybe.
what's your definition of being distinguished?
Well, there's some relative sense of distinguished. Because if they are orthogonal, you know they are
Yeah.
different. But I want the absolute way. We are allowed to compute entanglement quantities. But suppose we drop the label. So we know we have two states. They are orthogonal. But let's say Paul is the label of like this is a cup of coffee, this is a cup of tea. We don't tell you which is coffee, which is tea, let you drink it. And you tell me.
So you're not allowed to compute their overlap.
Oh, we are allowed, but it's a relative difference. You can say, oh, coffee tastes different than tea. Yeah, sure, they are different.
Yeah.
But which one is coffee? Right. And the first run argument would be, oh, we can distinguish them by energy of a Hamiltonian. But as I said, we don't have a Hamiltonian. And yeah, and so on. Yeah, there's many run arguments. If people want to put forward some argument, please. Otherwise, I'll continue. Okay, so my intuition actually, I came up with some guesses based on the two-dimensional thing. The two-dimensional chiral state on the disk. Well, we will ask the same question, but my intuition is that if we have a abelian anion, I sort of better understand this one. So like, yeah, let me skip this part and let me tell you my intuition. So if anion A, that's this there, is not abelian, I can distinguish tell there is an anion locally by looking at the correction to entanglement entropy. We have this linear combination of entanglement entropy, which was precisely the statement in axiom A1. Well, it gives you 0 if you have a vacuum state, but if you put a non-abelian anion, it turns out there's some correction log 2 log dA, which is greater or equal to log 2. This is some large number. So you can tell there is a non-abelian anion state there by looking at the box. So I would say, oh, we can distinguish those two states if A is not abelian. But what happens if A is abelian? That would conjecture that those are, you cannot distinguish them. So you can develop your perspective, which one is a vacuum. Yeah.
So when I said that I don't expect them to be able to distinguish them, all I meant was that you have an abelian algebra. So you're going to be dealing, your defects or these charges have to do with irreducible representations in an abelian group. And they're all one-dimensional. They're all unitarily equivalent. Whereas non-abelian ones, they would not be. But in that sense, I meant that the abelian ones, you shouldn't be able to distinguish them because there's a unitary that will always change them. And that's just like calling this coffee, calling that water. Right?
I see.
That's what
and your statement doesn't depend on whether the series is a free boson or not.
No.
The
pure
nice.
algebraic.
Okay.
Yeah, pure algebraic.
Good. So yeah, I'm excited about it.
If I'm understanding the context well, but yeah.
Okay. So for abelian anions, it's quite the opposite. So the anions pair in a box. If you have a and a bar purely in the box, the string don't touch the boundary, then I can come up with a shallow depth circuit to create the anion pair. The first layer is the pair creation, and the second layer to annihilate, but you don't want to annihilate back, but you shift it a little bit, annihilate the other pair, so you're left with the A and A bar in the end. And that finite depth circuit is considered to be a very trivial operation, and the two will be in the same phase, and you don't have this breaking of axioms. So from the entanglement bootstrap point of view, there's still nothing there in the box. So that I understand the box story, that's something I will feel very confident to say there's no distinction. But then when anion string touch the boundary, in principle, I don't know 100%, but I would like to conjecture that they are, yeah, we couldn't distinguish them. Yeah, that was the starting point that I got very curious about the answer to this question. And now let's go back to the one-dimensional case. The one-dimensional case, from condensed matter people's point of view, you can have some parallel topological order block to fill in the between. So I convert the one-dimensional problem to two-dimensional problem. So this answer, conjectures and the knowledge of 2D will be translated into something I can argue in 1D, but this non-abelian part becomes a conjecture because I no longer have the partition. I cannot do this partition anymore. Well, I can do this partition in this figure, but not in the completely squash the one-dimensional chain. So this one is a conjecture, this one is another conjecture. I couldn't, yeah, it's hard conjecture for me. So, but there's some supporting evidence. I think it's weaker than what Nima said, but I found from Nima's paper that is, if we consider the relative entropy between two states on a single interval, you have this nice formula, which alpha and beta, you can switch them without changing the value. So this relative entropy actually does feel relative. Yeah. So I like this result a lot. And I actually try to do something on the spin chain. And I ask Panajay people in Illinois for help in the field theory part. So I confirmed numerous results in some class of state on lattice. And I also checked that instantaneous modular flow, the state cannot distinguish them.
So there is an intuition as why this is correct. So I spent quite a bit of time trying to understand this intuitively. And the origin of it has to do with the fact that these coherent states have 0 delta S.
Delta S.
So you take the vacuum state, so this is a CFT on a cylinder. Look at a reduced state on a region.
Okay.
Then the state that we're creating, I'm just inserting that at the center of the radial quantization. The change in entanglement entropy of the region compared to vacuum is 0. It's because that unitary could be viewed as a unitary localized at every single point on the lattice. That's just a cartoon picture.
Actually, I heard Zhengchen telling me about this, maybe this story, maybe a toy version of the story. But one question I had is, when you talk about this intuition, did you work with the uncompactified free boson compactified?
Compactified.
Oh, okay.
Yeah, it was essential that's compactified.
Okay, I see.
I have not thought about non-compact boson. It's just like, I mean, yeah.
Okay. No.
But this is compatible boson with rational.
Yeah. I'll give you this particular example.
Right.
So this rational compactification radius equals the square root of 2 in condensed matter terminology, that you have bulk theory gap the topological order with Samion excitation. The fusion rule is this, and topological spin is I, half of the fermion. And I'm lucky to find it that wave function, analytic wave function you can put on the circle, which not only give you the ground state, but also analytical formula for all the tower of a primary. So I can test what I want to test. So the Nima's formula for fidelity also worked out. Instantaneous flow, it doesn't distinguish those. Well, and because of that, I began to be more ambitious. I really tried to come up with some local unitary. Yeah, well, in general, this sounds to be too ambitious for condensed matter people. We usually will be very happy if we find shallow depth unitary, but for simplicity in numeric, I tried on-site symmetry first. Very surprisingly, it worked out. So the lattice, not only the, well, I was doing the following. So I want to find the product of on-site unitary that swap 2 points, those 2 points, and I find some unitary, and I check how does this unitary acting on other primary. It turns out to a very high accuracy, even in finite size, the tower of all other parameters are swapped as well. This suggests something.
I don't understand. Can you say it again?
So I do the following thing in Mathematica. So I have a finite spin chain, maybe the its side, and you have I have this truncated version of this
Mhm.
lattice. I require the unitary to swap this point and that point.
Right.
And I find some unitary, I apply that unitary to other primaries,
Mhm.
and when like apply to this one and see whether it becomes this one.
Right.
It turns out it's almost
Oh, wow.
almost correct. So the entire lattice is swapped in some way. And this is the one case, and I tried another. This time I require 2 things. So this state becomes this one, and this state becomes the third one. It turns out the entire lattice is swapped like in a very simple way. I think it suggests that the affirmative answer that we don't really know which one is a coffee, which one is tea.
Right.
And you have relativity of the vacuum. And I'm very curious to what is implied. Oh, well, first of all, this is for free boson, but maybe it's beyond free boson, as Nima commented on that. That will be a lot more interesting because, for instance, the eating CFT, right? It has 2 billion primaries, like
Yeah.
one and side.
Yeah.
Yeah. Do we know which one is the vacuum? If we don't know, it's very interesting, right?
Yeah, that's right. That's right.
And another thing that based on our recent work on emergence of a Virasoro algebra, we expect to be able to reconstruct the Virasoro algebra from a single state. If we don't know which one is the true vacuum, then there will be 2 observers, which this guy said, oh, this is the right Virasoro algebra, and this is the vacuum has the largest symmetry. But the other observer will say, oh, this primary state is a true vacuum. So they disagree even on which was a set of conformal generator. And what does that imply in high energy, right? Those are the questions I'm curious about, but it's time to end, so I'll stop here.
There are a lot of questions. Are there more questions for Bowen?
I have a maybe a stupid question. So if I want to do an experiment on the side 1 and side A, there must be a way to tell them apart.
Side 1 and side.
Like the one without anion and the one with anion.
Yeah.
I mean, experimentally,
Yeah.
there's definitely a system whether there is anion or not.
Yeah, because in experimental setup, usually you have a preferred basis, like the system with translation or something.
Mhm.
Then you have more tools to play with to distinguish them.
I see.
Yeah, I'm talking about the case that you, up to local unitary, you don't know which basis is a better basis.
I see.
Yeah.
So
Oh, yeah,
okay.
my case is relevant for classifying based on matter in a gap state case. But for the gap state, I mean, yeah, we're still exploring what it implies. It may be something deep, but we are still thinking about it.
Sure, but you're saying that you don't have translations. If you do, then you have a preference.
I guess so, yeah. But actually those 2 states both have translation symmetry. And could be both have 0 momentum.
Are there any last questions? We have to leave the room. There's something going on in 5 minutes. Or is there a last question? Which last question? Of course, we can continue the conversation with one afterwards. Let's thank Bowen again.
Lime,